In this tutorial, I'm going to show you how to use the multivariate statistical analysis tool to analyze EELS spectrum image datasets. The sample I'm looking at this time is a multilayer of bismuth ferrite and iridium, grown on a strontium titanate substrate. The data is counting EELS data acquired using a K3 continuum. To perform PCA decomposition, make sure the spectrum image dataset you want to process is frontmost in digital micrograph and selected. Enter the data fit technique. Go to the MSA analysis palette and click Decompose to run the PCA decomposition. When the calculation is complete, the PCA decomposition is shown in a new compound object window, which contains three objects: scores, loadings, and the scree plot. The scores object is a data stack showing the spatial distribution of the principal components. The loadings object is a data stack of the principal components, and the scree plot is a log plot of the eigenvalues of the principal components. In all cases, the components are in order of significance. The most significant components are shown first in the data stacks and the scree plot. So starting at slice index 0 in the scores stack and the loading stack, and in the scree plot at 0 on the x-axis. To look through the data, click on the scores object and use the slice tool in the slice palette to change the displayed slice. The slice can be changed using the top slider or the spin control, as I'm doing now. This is a good way to screen the data to figure out how many principal components are needed for reconstruction. Look at both the scores and loadings whilst increasing the slice number. For this dataset, there is strong structure in the scores maps and the loadings up to component 4. The loadings have strong variance up to this point, but look at the form of the components. There's lots of negative intensity, and the components don't really look like energy loss spectra at all. Principal components above the fourth component contain pure noise for this dataset. The scree plot also becomes linear at component 4, which is important and we'll cover in the next section. To perform Varimax rotation, just make sure the PCA decomposition is selected. Go to the MSA analysis palette and click the Varimax button. A scree plot is displayed and the factor rotation options dialog also. Remember, the scree plot is a log plot of the eigenvalues of the principal components, and the components are in order of significance. The scree plot is initially non-linear, but we can see an inflection point after which the plot becomes linear. The linear part of the scree plot indicates the noise components, so we want to keep principal components that have lower index than this inflection point. The inflection point is at component 4, which is in agreement with what we saw looking at the data stacks by eye earlier. This sample has very uniform thickness, and we're using a K3 camera to perform counting EELS, which gives us very high quality spectra without detector artifacts. These two factors combine to give a dataset with very well behaved and linear statistics, which gives this very obvious inflection point. This isn't always the case for EELS data, so it's always worth looking at the data stacks as we did before, in addition to using the scree plot to identify the correct number of principal components. To make the loadings more interpretable, we want to make them non-negative, and to do this, the factor rotation needs to be performed in the spatial domain. Make sure spatial domain is selected, and then decrease the number of components as needed. I'm going to choose 4 components here. Click OK to perform the rotation. The software performs the calculation and puts the results in a new compound data object called Varimax Rotation. Now look at how the loadings compare to the original decomposition. The components look like energy loss spectra, which is much more useful for interpretation. Now PCA decomposition and Varimax rotation are covered, Let's look at the simple denoise. To perform a simple denoise, just select a spectrum image dataset, go to the MSA analysis palette, and click Simple Denoise. A scree plot and the data denoising dialog are displayed. The idea here is the same as Varimax. We want to use the scree plot to identify which are the important principal components and which are noise. As before, look for the inflection point in the plot, choose the number of components, and click OK when you are happy. A new dataset is created, which is a reconstruction of the original data using only the components we decided to keep, so we've performed noise filtering. Place a spectrum picker tool on the original data and then drag it onto the denoise dataset to create a mirror picker object. To compare the original spectrum with its denoised equivalent, just copy the denoise spectrum using the Ctrl and C keys, and then paste onto the original spectrum using the Ctrl and V keys. The noise has been removed as we'd hope. One thing to note here is that when we do a simple denoise, we don't end up with the PCA decomposition. So essentially the software is running the decomposition and then just doing the reconstruction.